Electric fields are created by electric charges. But what happens when those charges start moving? The answer introduces a second fundamental field of nature, the magnetic field. Without magnetic fields, electric motors would not work, transformers would not exist, and wireless communication would be impossible. In the previous lesson, we learned that electric charges create electric fields that exert forces on other charges. However, scientists discovered that moving charges produce effects that cannot be explained by electric fields alone. For example, when an electric current flows through a wire, a compass needle placed nearby changes direction. This behavior occurs even though the compass is not electrically charged. Something else must be influencing the space around the wire. The challenge was understanding what physical mechanism causes these effects. Why do moving charges behave differently from stationary charges? The answer lies in the existence of magnetic fields, a fundamental component of electromagnetism. A magnetic field is a region of space where magnetic forces can be observed. It is generated by moving electric charges, electric currents, and magnetic materials such as permanent magnets. The magnetic field is represented by the symbol B and has both magnitude and direction. Unlike electric field lines, which begin and end on charges, magnetic field lines always form closed loops. They do not have a starting point or an end point. One of the most important ideas in electromagnetism is that electric and magnetic fields are closely connected. Moving charges generate magnetic fields, and changing magnetic fields can generate electric fields. This relationship eventually leads to the formation of electromagnetic waves. Intuitively, imagine traffic moving along a highway. A stationary car simply occupies a location, but moving traffic creates additional effects such as airflow and turbulence. Similarly, a stationary charge creates an electric field, while a moving charge creates both electric and magnetic effects. Physically, consider a straight wire carrying current. Electrons move through the conductor, and their motion generates a magnetic field around the wire. The field forms circular loops centered on the conductor. This phenomenon can be observed experimentally using a compass or magnetic field sensors. Mathematically, the strength of the magnetic field depends on the amount of current and the distance from the conductor. Larger currents produce stronger magnetic fields, while increasing distance reduces field strength. This relationship forms the basis of many electrical and RF engineering applications. Magnetic fields are essential in RF engineering because they form 1/2 of every electromagnetic wave. Whenever an RF signal flows through an antenna, the changing current generates a changing magnetic field around the conductor. Transmission lines, transformers, inductors, waveguides, and antennas all rely on magnetic field behavior. Inductors, for example, store energy in magnetic fields, just as capacitors store energy in electric fields. At the system level, magnetic fields enable energy transfer, wireless communication, electromagnetic wave propagation, and antenna radiation. Understanding magnetic field behavior is therefore critical for analyzing RF circuits and communication systems. Electric fields and magnetic fields are often introduced as separate concepts, but nature treats them as two parts of a single electromagnetic phenomenon. Neither field alone can fully explain how electromagnetic energy propagates through space. A common misconception is that magnets are the only source of magnetic fields. In reality, every electric current generates a magnetic field. This means that magnetic phenomena are present in virtually all electronic and communication systems. Now that we understand both electric fields and magnetic fields individually, the next step is to see how they fit together. In the next lesson, we will explore Maxwell's equations and discover the mathematical framework that unifies all of electromagnetism. In this lesson, we learned that magnetic fields are generated by moving electric charges and electric currents. We also saw how magnetic fields play a crucial role in inductors, antennas, transmission lines, and electromagnetic wave propagation. In the next lesson, we will explore Maxwell's equations overview and discover the four fundamental equations that unite electricity, magnetism, and electromagnetic waves into a single theory. If you found this useful, Like the video, subscribe, and follow for the next lesson.